So can you see my screen now?
Yes.
Okay, great. So in fact, I hope to be brief. So we recover the original schedule. What I want to present is some work we have done. I mean, apart from the work we have done together with Ricardo and Ricardo and Mark, and in the part of the I mean, work package 3, we also have been contributing to work package 1, and this is the work I wanted to present because I think I have not presented before in any ExaQUte meeting. In fact, I have presented it in a congress, but not in this context. So I think it's an interesting work that some of you may be interested in. So the idea is to talk about embedded. Okay, first of all, I made a small mistake when sending the title, and I forgot to add this random word in the workshop in the workshop summary. So the idea is that we want to develop, or we have been interested in developing embedded methods in combination with multilevel Monte Carlo, not only for complex geometries, but also including randomness in the geometries. Okay. So this is the outline. I will, as I said, try to be brief. I don't know how successful I will be, but anyway, I will talk about the multilevel Monte Carlos, and then I will spend some time here talking about embedded methods, a couple of examples and conclusions. So I remind all ExaQUte partners know this, but maybe it's worth to keep in mind that we want to do UQ and stochastic optimization, but our target is always geometrically complex domains, and the project essentially it's made of the combination of these ingredients: multi-level Monte Carlo for UQ, embedded methods, adaptive mesh refinement, which we have been listening right now, HPC, and the dynamic task scheduling developed by some of the partners, BCC and ET4I. So I will focus, as I said, on embedded methods, and the reason why we want to use embedded methods is that because they are very useful to deal with complex geometries. Here you have an example of the kind of problems we want to face. And in particular, I would like also to mention that in some of the cases, we have also uncertainty. So for example, if we are interested in a particular building, we may know the geometry of that building very well, but we can have some uncertainty in the rest of the domain of interest for solving this problem. So our goal is, as I said, to deal with complex geometries, but also random geometries, and therefore we take this model problem. I will include some equations, but very few of them, or I will try to find an equilibrium. The idea is in this work is we took the Poisson problem. Here you have the Poisson problem with some force. Everything can be stochastic here, but our goal is to consider stochastic domains. So domains which contain some uncertainty, and this is the goal of this talk, and this is the goal of this work. Not only to deal with boundary conditions, but also or forcing or coefficients, but also the shape of the domain to be uncertain. As usual, we want to take some quantity of interest. The quantity of interest could be, for example, to fix ideas, the average of the solution on a part of the domain. So if we have an uncertain domain, we would like to compute this value on a subdomain. There's a slight detail here that is important, because if you have a random domain, this is one realization, this is another realization, maybe only for some subregion this quantity is well defined. So that's why this is one we will use. And the issue is that we want to compute some statistic of it, fix the expectation or we want to approximate the expectation to fix ideas. We know that this problem, or the UQ in general, suffers the problem of the curse of dimensionality, which is the exponential growth with the number of stochastic dimensions, and this is a problem. So there are three main families of methods. We all know that since the starting of the project. We have the stochastic alerting that is based on some kind of polynomial expansion. And a closely related technique is a stochastic collocation, but we favor sampling methods because in particular, multilevel Monte Carlo is one of them. Monte Carlo is another one, because precisely they permit to break the curse of dimensionality. Okay, so that's that. We will come back. I will come back to this later on. But what happens? The question is, what happens when we have an uncertain geometry? Well, when uncertain geometry, the situation is a little bit particular. So there have been other techniques, and other techniques are essentially, there have been essentially three techniques to deal with problems in which you have uncertainty in the domain. One of them is to use domain mappings. So if you have a family of different domains that you can describe by mappings to a standard one, then you can perform any kind of uncertainty quantification. So for example, you have a reference domain, and then you have one realization, and then you have another realization. As soon as you can define maps, that's okay. You also have perturbation methods. Perturbation methods is quite simple. I mean, it's a bit different, but similar idea. You have an original base geometry that you can perturb, and this is another way in which geometric uncertainty has been managed. They are both somehow limited by if you want to apply them to general situations, because as you can imagine, defining mappings is restricted. You cannot change the topology. Perturbation is also restricted in as much as you have a base case. And then you have embedded methods, and so far embedded methods have seldom been used. In particular, there's a reference by Canuto and Consubek on 2009, and combining embedded methods with stochastic alerting. But we have seen, serving the literature, that first of all, there have been no applications to 3D problems, other than there's an exception, which is a study that has been done with the flow in a box, in which you have one wall that is uncertain. So, for example, if you have a turbulent flow over a plate, then there were some technique to introduce uncertainties in the roughness of that wall. And one important point here is the robustness issue that is an issue we will talk about during the presentation many times, because I mean, if you fail somehow on compute just one sample, then your whole UQ estimation is missing, because you cannot neglect samples. If you neglect samples, you are introducing a bias. So that's a very important point in particular in this case. So what we have done? Well, multilevel Monte Carlo. Multilevel Monte Carlo means that we will compute a quantity of interest, and we will repeat that computations n time, and then we will approximate the expectation by the sample average. And the issue is that to compute each of them, we need to generate a random input. And in our case, a random input means to compute a different discretization of the domain, okay, if you want to deal with geometric uncertainties. So what are the good news and the bad news about Monte Carlo? Well, these are our starting point. I mean, the MC method precisely is dimension independent, so it does not suffer from the curse of dimensionality. is non-intrusive in the sense that you can do what we are doing in the ExaQUte project, programming the method on one side and programming the sampler from the other, and also we can exploit parallelism between samples, and therefore that's the reason why we like it. However, there are some drawbacks, and these drawbacks are non-optimal complexity. We know how to deal with this. It's essentially multi-level Monte Carlo, and this is an issue. The issue is that random domains. If you have randomness in the geometry, then you need different meshes for different samples, and that's a very serious problem. There's also the problem of robustness. So, for example, if the domain has some complexity in the geometry, and you are not able to mesh one of the cases, then you have this robustness issue. So the extension to deal with this drawback here is to do multi-level Monte Carlo, and in multi-level Monte Carlo you have a hierarchy of meshes. The ideas that we exploit is to introduce. We take ideas from multigrid and we introduce a hierarchy of meshes, and the essential easy idea is to transfer part of the complexity from fine meshes to coarse meshes. And therefore, what we exploit is the linearity. For example, if you are interested in the expectation, we can approximate the expectation by essentially performing a kind of weighted average, if you wish. So the final complexity of multi-level Monte Carlo depends on the number of levels and on the number of samples you take on each level, and it turns out that you have to carefully choose them. And here we have a lot of work from EPFL. So these are the assumptions Ricardo mentioned in his first talk. You need, for the multi-level Monte Carlo to work a decay of the error in computing the expectation that depends on with the mesh size and also of the variance, and you need a given increase of the cost in terms of the number of degrees of freedom. And so with this hypothesis, you can obtain the number of levels and the number of samples you need. But the point is that this number of samples and the level depend on some parameters that you can predict for elliptic PDEs, but are not known in general. So that's why the EPFL group has a lot of work on trying to estimate these parameters on the fly, and most of the continuation multi-level Monte Carlo methods, this is what they do. I mentioned this because, well, I will let you know why I mentioned this later on. So with multi-level Monte Carlo, what we have done with multi-level Monte Carlo, let me go back to the Monte Carlo. We managed to make it more efficient, to make it optimal, essentially. So complexity is far smaller than MC. In fact, can be made optimal. I'm not that happy with that, because the price to be paid for that is the introduction of the mesh hierarchy, together with the rather more complex choice of the number of samples on each level. Okay, so that's why we are happy, but not that much. And we still have these two main issues, which are the problem of generating the meshes, which in general, is not an issue because you generate the hierarchy once and you are done. But if you have uncertainties in the geometry, then the geometry will change from sample to sample. So you need two meshes for each sample, and that's an issue. Okay? So that's why, and here is where embedded comes to rescue us, because we can consider a hierarchy of meshes together with embedded method. But we still have the issue of robustness, and that's precisely what I will talk about next. Okay. Why? Well, let me to explain why this robustness issue is important. I would like to give you a brief overview of embedded methods. What is this embedded or unfitted? Sometimes they are talking unfitted because the idea is that you have a domain, you can generate a mesh of that domain. This is a body fitted mesh, a mesh that is that has edges on top of the boundary of the domain. So it is the boundary of the domain. You have edges of the mesh placed over them. I mean, over that boundary. However, in unfitted methods, what you want to do is not to do that. You want to use a background mesh and to draw the domain on top of it, and then to be able to do the calculations without having edges on the boundary of the domain. And therefore, which are the problems? What do we need to do this? Well, we essentially need three ingredients. We need to solve the issue of boundary conditions. We cannot impose a strong boundary conditions, but I mean that's something that is solved already. We know how to do it, and the solution is to use imposition of weak imposition of boundary conditions with a niche technique. So this is something that is known, and we know how to do it. The second issue is the numerical integration. I mean, I'm not saying that these are things that are easy to be done, but they can be done. Especially numerical integration requires some kind of essentially cutting the elements. So, for example, I don't know if you zoom here. If you zoom here, then you have the element. You have the interface here. You have to integrate here. So you need somehow to cut the elements, but you can use some kind of templating to do that, and that's so. This can be done, and this can be done. The problem is something that is not actually was not really understood for a long time. It has been recently characterized, which is called the small cut problem. Okay? What is the small cut problem? The small cut problem it's a problem, you see it has been completely defined a couple of years ago. The small cut problem is the problem that appears when you have an element of your background mesh and you have a cut of that element an intersection between that element and the actual domain that is of a very small size. In practice, this size can be even much smaller than the size of the mesh. So when this epsilon is much smaller than the mesh size, or in other words, when this region is really small, then this can cause the break of the calculation. Why? Because it has been proved, or the full characterization of that problem is that the condition number of the system you have to assemble and then solve exploits with when this goes to zero, which is actually easy to understand because, for example, if you think about this degree of freedom, okay, this degree of freedom here is not connected to any other degree of freedom than this one. So in the limit of this region being too small, the value of the function in this degree of freedom is essentially unknown, and that causes the matrix to be almost singular. Okay. So one solution for that problem has been developed by the group a couple of years ago, was to use a technique that we call aggregation. And we also have the traditional h-2 condition number of finite elements, but this is a standard, and we know that can be managed by domain decomposition or multi-bit or whatever. So what's the idea of the aggregation to solve the small cut problem? Well, the idea is the following. The idea is we have some DOFs, some degrees of freedom that are well posed, those that are inside the domain. So here I have the domain, and here I have the exterior. And some problematic degrees of freedom, which are the degrees of freedom that are out of the domain that potentially are not connected to any other. In fact, not all degrees of freedom that are seen in this slide are problematic. So, for example, this one is not problematic because even if this volume is very small, this degree of freedom will still be connected to this one. So, actually, the ill-posed degrees of freedom or the problematic degrees of freedom will be those that are only connected to interior degrees of freedom by cells that have a small field. Okay. But anyway, this is a detail, and in general, what we can the idea of the technique is the following: let us eliminate these degrees of freedom. We don't need them. We don't need them because remember that we want to describe functions inside the domain. Because we want to describe functions inside the domain, we don't need a function that is 1, 0, and 1 here and 0 here. But what we can actually do is rather to extend the functions that are defined on this element to be defined to all this region, forming what we define as an aggregate. So the idea is that now you can have, for example, if you have a function that take values 1 in all these nodes, that function will look like this. Okay, so instead of being this one is the original. So this is the finite element function that you will have if you put 1 in all these 4 nodes. Then it will be 0 in all the adjacent elements. Here, by eliminating these degrees of freedom, you will obtain this function. And how do you eliminate these degrees of freedom? By imposing constraints in the same way as you do when you have hanging nodes in a refined mesh. Okay. So that's why the aggregated technique permits to deal with the small cut problem. That's what we did. So a couple of words about the implementation. You know that we had this our FEMPAR software, which was written in FEMPAR, and we found it. I mean, we not develop an interface to the dynamic scheduling. So essentially, what we have done here was a simple implementation of multilevel Monte Carlo to learn a little bit about how to deal with these embedded methods. Why? Because in this FEMPAR we have many techniques that we need. We need the unfitted discretization. We need the well, I mean, we have this, although we have not used here, and we have the solvers. So we have the unfitted aggregated discretizations, and we also have the solvers that permitted us to have scalable solution. So we made a quite simple implementation of MLMC. I think we have some ideas that can be exploited for other kind of schedulers, more general ones. Ours is something that is very tailor-made for this program. So what we did was essentially to work at the MPI level, partitioning, and we are trying to summarize the implementation, and I think it can be interesting for many of you. We can discuss it in separate talks, but the idea is that what we do is to essentially proceed level by level, sampling first those levels that require more processors. So if you here have I don't know 8 processors, then we first sample on the finer levels, and then we proceed level by level. But we can mix levels because we have this implementation that is made essentially for us. So first example, or the first of the examples we have run is a simple one, a very simple one, just to check that everything was okay. Imagine that you have the solution of the Poisson problem on a disk, and that disk has a radius which is a random number. So you have one realization, which is here the one in red, and the radius is sampled from a uniform discretization that has a minimum, a truncated uniform discretization. So the smaller domain we can consider is this one, and the larger domain we can consider is this one. Okay, and therefore when we go sampling, we get different domain sizes. And what we do here is to use a background mesh, well, a background hierarchy of meshes. But first of all, what we did was to check that we get the slope, the appropriate slope, and this slope is the slope. I mean, that is predicted by the MLMC theory in the case of elliptic problems. And we check that we have actually the convergence for the mean, for the variance, And when you go to the computational cost, we also verify that we have the required computational cost, which is this, but only when you go to find grids. So for coarse grids, you know, the estimate, the solver is not dominating. So this assumption is not that good. So the finding is that actually we need the complex technique that have been developed by APCL, because just fixing the number of samples in terms of theoretical estimates will not be optimal. Okay. So this is the next example, and the most interesting one in my view. This is a typical example that is used in the literature about embedded methods. It's called a popcorn, okay, and it's defined by a level set function in the following way. You have a sphere, and that sphere has on some positions smaller spheres added to it, okay. And the idea is to solve the Poisson problem in this domain. So what we did was to define a stochastic popcorn. That is, instead of consider a sphere with some small spheres of fixed position and radius, we decided to take some parameters, some random parameters, in particular, the number of spheres, the position of the, I mean, this is the main sphere, the position of the main sphere and of the big one and the radius, and the positions of all these spheres and all its radius. And what we got is, so here you see the different domains. That is completely, I would say, completely random, as you see. And in all the cases, we are prescribing a forcing term. So this is a manufacturer solution. We prescribe the right-hand side to get a given function. That's why you see always the same colors with a different geometry. We found for different quantities of interest different convergence rates. So that's why it's important to have some kind of, this is for the mean and this is for the variance. And that's why it is important to have, and this is a computational cost, and that's why this is important to have this kind of adaptive MLNC. We implemented one, maybe not the better, but okay, we verified that at least the computational cost goes as expected, more or less, even though this curve is not that. This is for one quantity of interest, and this is for the other. So at least we have the expected cost increase with the error decrease. However, here is the important point I wanted to make about the robustness. So what you're seeing in this slide is the number of conjugate gradient iterations. This is for the two-dimensional version of this problem. We have defined this problem in 2 dimensions and in 3 dimensions. So this is for the 2-dimensional version of the problem, and what you are seeing here is the mean value, the average number of iterations. This is the minimum number of iterations and the maximum number of iterations among samples for different mesh sizes. And what you see is the standard technique without aggregation and the technique with aggregation. So you see here how different the computational cost is depending on whether you use aggregation. In 3 dimensions, we cannot plot the same in the same figure because you see here the scale. This is for without aggregation, and this is with aggregation. So here is where the robustness issue becomes apparent. So I think I am taking a lot of time. So we have some speed up, strong and weak scaling, but that's not the topic of that talk. The last point I want to make is that with this technique, we can also handle random topologies, and that's a very difficult problem because the problem here we solve is a plate that has 2 holes, and we want to compute, say that this is a heat transfer problem. So you heat from this side, and you want to know how much heat transfer from one side to the other. That depends on the holes you do. So imagine that we do random holes. I mean, some randomness in the position. You see that there are some cases in which you have this kind of topology and some cases in which you have this kind of topology. So this change of topology makes this problem impossible to be solved by either domain mappings or perturbation methods. The only way to deal with these problems is with the kind of techniques we are doing here. So in particular, you might be interested in the heat flux in terms of the radius of the holes. So very quick conclusions, not to take a lot of time. We think that the combination of embedded and multilevel Monte Carlo is a good way of doing UQ in random domains, because for body fitted methods that would be, we think, almost impossible, or at least very difficult. Other methods have not been able to deal with 3D problems or complex geometries. But we need to do embedded method with some careful discretization, and that's why we consider that this is an important contribution to of the whole ExaQUte project, because that was actually devised at the beginning. So that's it. Thank you very much for your attention, and I'm ready to answer the question you might have.
Thank you, Javier.